Hey, good afternoon, everybody. I'm Dave Aronson, the T-Rex of Codosaurus LLC, and I'm here today to tell you about a new, short, simple, free, low jargon, technology-agnostic definition of software quality, and some tips how to achieve it. So let's start things off with a question. Let me know if you like low-quality software. Anybody? Anyone? Bueller? Okay, let's try another question. Have you written any low-quality software? Yeah, I think we all have. I sure have. So we've got a lot of people writing low-quality software, but we don't like it. So it seems pretty clear to me that we need more software quality. But that brings us to just one tiny little question. What is it? If we don't have a good definition of software quality, we can hardly hope to improve even our own, let alone advance the whole state of the art. There have been previous attempts to define software quality, but when I was looking for a good definition a few years ago, I didn't find anything I really liked. Most of them had assorted problems. A lot of them were long lists of complicated terms full of developer jargon. Now, jargon is fine for when we're talking amongst ourselves, but I wanted something that other people would understand, even completely non-technical people, well, at least technical enough to use a computer, so that they could have a better understanding of what we do and give us more precise feedback about exactly how our software sucks. And you know most of it does, right? Some of these definitions were proprietary, forcing us to buy expensive tools, or at least relatively expensive documents. Some were only applicable within the context of certain technology stacks, usually, again, proprietary. But I felt that was just wrong. I wanted something that everybody could use for free. Some definitions focused exclusively on the aspects of interest to us developers, ignoring the needs of the users and the other stakeholders. For instance, many were completely about maintainability, which nobody else cares about, at least directly. And they omitted other important things like whether the software was easy to use. Some definitions weren't even really about the software itself at all, but about the process and its byproducts, saying you must hold these meetings and produce these documents. Now, some of these meetings and documents and such may be very helpful, but to make that your definition is a one-size-fits-all prescription. And if any of you have any one-size-fits-all clothing, you know how well that usually works. So I wanted something that was more flexible and more focused on the software itself. Long story short, I didn't find anything I liked or that was widely accepted, so in the spirit of XKCD, I decided to make my own. It was clear that I had to address this at a very high level, so I zoomed out from down in the weeds where we developers tend to live, up past the 40,000 foot view to about low Earth orbit. And that let me boil it down to just 6 aspects, a list so short that it literally fits on the back of a business card. And as proof, here's mine. You can come up here and get one as your own little mnemonic cheat sheet after the presentation. It also let me take into account the wants and needs of not only us developers, but other stakeholders such as the users who will be using our software, the customers who will be paying for it, who are not necessarily the same people, and others such as our colleagues. And again, I mean not just our developer colleagues, but for instance, our management, from immediate supervisors up to the boardroom and operations, QA, tech support, and so forth. I call this new definition ACRUMEN. But what does that even mean? Originally, it was a Latin word meaning sour fruit, like grapefruits, limes, and especially lemons. And that's why you'll see lots of lemon yellow all throughout these slides. So I'm taking those sour lemons that life often hands us, frequently by the bushelful, sometimes in the form of low-quality software. And I'm making what I hope will be delicious lemonade in the form of ACRUMEN. Which brings us to the question, what is that? The acronym ACRUMEN, try saying that 10 times fast, simply takes those aspects I spoke of and puts them in priority order. And by now you're probably wondering, so what are those blankety blank aspects already? Yes, I see some nods out there. They are, at long last, that software should be appropriate, correct, robust, usable, maintainable, and efficient. And don't worry about taking notes on this. As I said, I've got these mnemonic cheat sheets up here. Plus, after that space over there gets filled in, as you've probably guessed is going to happen, that's the big takeaway slide you can get a picture of. Anyway, what does all this stuff mean? First and foremost, software should be doing what the stakeholders need it to do. In other words, do the right job. And it needs to be doing that job correctly, or to make a bit of a play on words, do the job right. Then come a few aspects that are a little fuzzier, but I'm going to wrap more solid definitions around them. First, it needs to be hard to make it misbehave or malfunction. And again, I'm going to talk a little more about specific kinds of malfunctions that are of particular concern. However, it must be easy for the users to use and for the developers to change. The other way around, not so much. You generally don't want your users changing what your software does. And if we find our own software easy to use, but we're not the target audience, well, who cares? Excuse me. And lastly, dead last, despite how we technical people tend to worship this, it must make efficient use of resources. Now, I've said there were 6 aspects, and you see 6 up there, but ACRUMEN has 7 letters. So what does the N stand for? Does anybody want to guess? I'll give you a moment to get a picture of that. A big takeaway slide. Okay, I had considered actually various things like, for instance, not evil. But I'm sure we can all imagine some otherwise high-quality software being used and perhaps even designed for an evil purpose. I couldn't come up with anything, so it stands for nothing. I just tacked it on to make a real word, even if an obsolete one. Now, while this list is fresh in our minds, I will answer the second most frequently asked question, which is ACRUMEN, or at least ACRUME, always the correct ordering? Because there seem to be a lot of projects out there where the priorities are probably a little different. And the answer is no, it's not always ACRUME. Your mileage may well vary. Take, for instance, a purely internal number crunching engineering command line tool to implement some algorithm that's not going to change, like a basic law of physics. It still needs to do the right job, but maybe we don't need a precisely correct answer that would take a long time to generate. Maybe we can make do with a rough approximation. It might not need to be quite so robust because it's on the command line rather than having a web interface, which would be so easily abused, and there are fewer things to go wrong with it. It might not need to be quite so usable because it's a purely internal tool. Might not need to be so maintainable because it's not going to change. But if it's crunching a lot of numbers, it may need to be quite efficient. So its list may look more like this, ACRUMEN rather than ACRUMEN. The only real constant is that appropriate will always be at the top. Why? We'll see that in just a moment. Now we're going to look at each aspect in more detail, keeping in mind though that each of these is such a big topic that to even significantly scratch the surface would take all week, if not all year. And of course, our first aspect is appropriateness. If we don't have this, then nothing else matters. If our software is doing the wrong job, it doesn't matter how well it's doing the wrong job. So appropriateness is not only more important than any one of the other aspects, it's more important than all the rest of them put together. And yet, we developers are generally not taught that this is even a thing, let alone one that we need to be thinking about. To prove the importance of being earnest and appropriate, let's try a little thought experiment. Suppose you want a program to play checkers, and I write for you the world's greatest chess playing program. Now we can suppose it's going to be as correct, robust, usable, maintainable, and efficient as anyone could possibly ever want. But are you going to be happy with it? Yeah, I hear a no out there, a couple of head shakes, yeah. But why not? If it's so correct, robust, usable, maintainable, and efficient, why wouldn't you be happy with it?
It's not what you needed.
Exactly, it's not what you needed, it's not what you asked for, it's not checkers. In ACRUMEN terms, it's not appropriate. So I think that pretty well proves the case that appropriateness outweighs all the rest. So now that we know how important it is, how do we achieve it? In an ideal world, we could bring in the experts, and in this case, that would be requirements analysts. However, on this planet, we don't usually have that luxury, at least outside of working for huge companies. But we can use some of their tools and techniques. Primarily, we can go talk to the stakeholders, ideally face-to-face or as close to it as we can get. We can ask what they want and keep breaking it down into smaller pieces until it's something very easy to do. We developers should be very good at that. It's basically what programming really boils down to. But we should go a step further and ask why they want things. That will help reveal what they need, not just what they want. And what they need is what we really need to satisfy. Once we've got a good grasp of their needs, we can show them mock-ups and prototypes of what we intend to do and demos of what we have done. This will give them an opportunity to correct our wrong ideas about their needs before we've gone too far in the wrong direction. Has anybody else spent a lot of time implementing the wrong thing? Yeah, I see some hands out there. I think we've all done that. Now, ideally do this periodically as sort of a continuous course correction. There's another thing though that I'll be returning to over and over throughout this presentation. We can propose tests. In particular, I recommend the given, when, then format, which is given these preconditions, usually data being in some state, whether it's an object or database records or whatever, when this happens, usually some kind of user input or signal from a sensor or a timer or another program or whatever, then this is the result. Usually the data being in a different state or something the user sees on the screen. This makes a great link between the worlds of business and technology because usually they can understand it and we can turn it into a test. Our next aspect, by the way, if you have any questions, feel free to raise a hand. Our next aspect is correctness. If our software doesn't have this, then pretty much by definition it has bugs. That's the primary alternative. It could be giving results that are obviously incorrect, or worse yet, subtly incorrect so that we don't notice so soon. It could be putting data into the wrong records or files, or deleting the wrong records or files. Nothing can actually stop us from writing code that has bugs. There have been various attempts to make bug-proof languages and bug-proof programming environments. They've usually turned out to be way too restrictive to be at all productive, even worse than debugging horribly buggy code. So our code may well have bugs, and the big question then is, just like the thermos that keeps hot things hot and cold things cold, how do we know? Anybody want to guess? Well, that's what I mentioned just a moment ago.
Insulated. It keeps hot things hot, cold things cold because it is insulated.
Well, I meant anybody want to guess how we know whether our code has bugs.
Actually, I know, because our users tell us.
Okay, that's one way, but ideally you don't want to let it get to the stage of user complaints. The way you catch them, yes, the way you catch them much earlier than that is to test them. The tests will tell us whether our code has bugs, assuming, of course, that the tests themselves are correct. Even then, though, that's not quite correct, but I'll get to that in a moment. Ideally, our tests are automated, which makes them a lot more reliable, repeatable, and maintainable than manual tests, and gets us vital feedback while the problem at hand is still fresh in our minds. Assuming, again with the assuming, can't really escape that, but assuming that our tests are reasonably efficient. We can start with the tests that the stakeholders approved for the sake of appropriateness, and these are likely to be high-level tests, like end-to-end system tests and a bunch of feature tests. That's not all we need, though. We should also have an assortment of low-level tests that we make up as well, such as unit tests and integration tests, to make sure all the little pieces work well individually and together. But even with all of that, these normal kinds of tests will only verify the correctness or disprove the correctness, whatever, of the cases that we thought to test. But there are some advanced techniques that can help find the cases that we didn't think of. For instance, property testing tests whether some desired property of our code holds true for all valid inputs, what formal computer scientists might call an invariant. A property testing tool will make up lots and lots of random data to feed into our program, and if it finds a test case that makes our desired property fail, then there's an edge case that we did not consider. Usually if it finds an invalid case out of a huge spread of data, most of them will try to narrow it down and help us find right where that edge is. Another advanced technique is mutation testing. That's a real fun one. Mutation testing runs our tests against slightly altered versions of our code. And if any version does not make at least one test fail, then it means that either our code is not meaningful enough, that the mutation actually changed the behavior of the code, or our tests are not strict enough to catch the difference that the mutation made, or possibly both. And by the way, I'll be speaking on mutation testing at NDC Oslo next month, if anybody's going to that. Anyway, we should have enough test coverage through various techniques and levels and kinds and whatnot to have strong confidence in the correctness of our code. Next up, we have robustness. If our software doesn't have this, then at best, it may show a lot of uncaught error messages and seem fragile and unreliable. Or it may crash a lot and actually be fragile and unreliable. Or it may get hacked because robustness includes the concept of security. The short explanation is that it's hard to make it malfunction, but what does that even mean? There are a few other things, but the vast majority of what I mean by this is covered by a core concept of information security, the CIA triad. Now, it's nothing to do with spies and gangsters. It's this triangle here of confidentiality, integrity, and availability. So, robust software does not reveal information when it's not supposed to, alter information when it's not supposed to, or become unavailable when it's not supposed to. Some people would also say it should not become available when it's not supposed to, but so long as it doesn't violate either of the other two, then it's usually not quite such a big deal. It may be a resource drain, or it may be operating without some other security safeguards that are not available at that time, but usually it's not a big deal. Anyway, a robust system should uphold these principles even when under attack by someone trying to force it to violate them. So, sounds like a tall order. How do we achieve all that? Once again, we could bring in the experts. And in this case, that would be penetration testers, or for short, pen testers. The good news is you don't have to work for a huge company to make use of them. Now, a huge company may have some of their own, especially if the company is in the technology space, but there are a lot of them working for small independent computer security companies that you can hire through a contract. They're great for testing entire corporate networks or very large or sensitive systems, especially security systems. The bad news is, well, there are several pieces of bad news. They can be rather expensive. They can be quite disruptive because they pretty much have to test the production network rather than the development or test or staging environments. They don't usually report about every little piece that was not robust, just the things that were used in a successful chain of attack to more or less completely take over your system or whatever kind of objective you set for them. And they're usually called in, this is not their fault, but they're usually called in after the system is complete, or at least we think it is, rather than earlier when the system would be easier and cheaper to change in accordance with their advice. Better yet, they could even be brought in as an ongoing part of the process to tell us what direction to go in, at least robustness-wise, rather than having to have them just correct what we did wrong. But once again, we'll generally have to do without them. However, we can once again use some of their tools and techniques, especially software such as static analyzers, which simulate the execution of our program, fuzzers, which test our program's reaction to various kinds of possibly invalid inputs, and probes, which test our system for vulnerability to specific known attacks. Many of these are even available as open source. Even without their software, though, we can go a long way with just their mindset. The huge part of this is to ask ourselves, what could go wrong? And here the tone of voice is very important. It's not what could go wrong, as though we don't think anything could. It's more statement-like. What could go wrong? I'm just trying to list it out. I don't need a demonstration, thank you very much. For instance, if the system wants a user to type a file name, the user could type the file name incorrectly. Or they could type correctly the name of a file they don't have access to, whether you're trying to read it or write it or whatever you're trying to do. The program should not crash or display something cryptic like "enoent." just because the user typed a bad file name. It should show a friendly error message and let him try again. In fact, most users would probably not even know what NoVa means. Any of you? I'm not seeing any hands, so even within, presumably most of you are developers, it's basically short for E for error, no directory entry, very cryptic way of saying file not found. So, you see what I mean? Don't give something that cryptic, even to developers, let alone non-technical end users. There may even be external factors that we should handle, like losing the network power, the network connection or the power, whether our end or the users or somewhere in between, or even a third-party service we're relying on. These are things that, of course, they're not exactly expected, but they are reasonably likely, and we should handle all reasonably likely scenarios as gracefully as possible. Now that may sound like a lot, but we're just getting started. We've only talked about things that are innocent mistakes and mishaps. To make it really robust, we have to make it secure, which means we have to think like an attacker. We have to ask ourselves, what are the system's weak points? What can an attacker make happen that will open an opportunity for them to get just one tiny step closer to their goal? And in what unusual ways can someone get information out of or into our system? So we should brainstorm on these and write down a huge list of anything within reason that we can think of. I was once brainstorming the threat scenarios for an information system, and they had things already listed like t.hack, possibility that somebody might hack in. I put t.rex, the possibility that a dinosaur would rampage through the data center. But that didn't make it into the final list. I wonder why. Anyway, for everything reasonable that we come up with, we must then handle it. I know that's extremely vague, but how to handle something is going to vary very widely depending upon what exactly it is you're trying to handle. User types the file name incorrectly, ask him for another one. But if the system detects that, for instance, there's an attack in progress and data might be getting corrupted, the appropriate response may well be to shut the whole thing down and not start it up until someone physically goes into the data center and pushes the big green button. In between, there are, of course, lots of possibilities. We can make the situation much less likely to happen, maybe even prevent it completely. See if we can somehow mitigate the negative effects or recover from it, or even just accept it or take out insurance if it's not too horrible. But whatever we decide to do about it, we must test it because it's now an important part of our system. Next up, we have usability. If our software doesn't have this, then the users will be frustrated and may stop using or recommending our software. That could be disastrous for a software vendor like our hosts today, Microsoft, or a software as a service company, which, come to think of it, nowadays Microsoft is as well. Hard to use software can also lead the users to do the wrong thing. You may remember, I think it was last year, maybe the year before, Hawaii had a false alarm about an incoming nuclear missile. That was because the software made it not very obvious how to do the right thing, to send out a test message instead of an actual alert. Unfortunately, if we Google software usability, oh, excuse me, forgot where I was. If we Bing software usability.
If we look up better.
There you go. Let's keep it technology agnostic. If we search for software usability, a lot of the stuff we find is about ensuring that users with various challenges can use the software about as easily as the rest of us. In other words, accessibility. Now, that's part of this, and it's a wonderful goal all by itself, but mainly I'm adding on that it should be easy for everyone, not just equally difficult. So to start defining it in more depth, it should be clear at all times what the users can do, should do, and must do, how they can do it, and what else the system can do for them, especially any help facilities, and all of that should be easy to do despite any challenges the user may be facing. We can start with the things that accessibility is usually about, such as poor to no vision, color vision, which is a big challenge of mine, lack of hearing, or fine motor control, such as to use a mouse or trackpad or touchscreen. But there are many other challenges we should still be aware of, like the lack of literacy, at least in our character set. I can understand a little bit of Japanese, but only spoken. If I were to use something with an interface in written Japanese, I'd have no idea. It might as well be Greek. There are other sorts of cultural literacy the users might be lacking. If they've spent their entire lives in a rural village with no traffic lights, they might not understand what that thing is, or even the implications of the colors. We think of red for stop, green for go, yellow for caution. They might not even know that. And lastly, the users may even be of low intelligence. Yes, we may joke about stupid users at times, but statistically, about half of them will be below average. Also, there may be environmental factors again. Imagine someone using your mobile app on a small phone while standing up in a crowded bus in downtown rush hour traffic. Accurate tapping is not going to happen. And an often overlooked part of usability is that all software needs to be usable, whether it's a web application, a mobile application, a desktop GUI application, a command line application, or an API, whether it works through function calls or a wire protocol, whether binary or text-based or whatever. That's a lot, isn't it? So, how do we achieve all of that? As you may have guessed, once again, we can bring in the experts. The bad news is, as kind of implied by already redefining this term, a lot of the people we find if we search for usability experts are really going to be accessibility experts. The good news is, though, we have a very wide range of other professions that have various kinds of training that can be very helpful to us. We probably really want a user interface expert, or better yet, a user experience expert. But it might be a lot easier to just get hold of even a web designer, or even an old-fashioned print graphic designer, because they still have some training in some basic principles of practical visual design, assuming that our software is mainly used through a visual interface. But however, we'll still usually have to go it alone. But we can go a fair distance by applying their principles. For instance, here we see an application of the KISS principle, meaning keep it simple, stupid. Or if you don't want to be so negative, keep it super simple. Note the simple ease of use from the companies with a reputation for good, clean user design that makes it easy to use, as opposed to the cluttered mess from your company, which for most of us is not anything anywhere near as successful as Apple, Google, or of course our hosts, Microsoft, which has been getting pretty good at user interface lately. So, sorry not to have one in there from Microsoft, but this was somebody else's creation. So, oh well. Another thing we can do, if the software is something we can use ourselves, is to do so. In other words, dog food it, eat our own dog food. But remember, if we find our own software easy to use, that doesn't mean our users will. We have inside knowledge that makes it a lot easier. But if there's anything we find difficult or unclear, it'll be even worse for our users. So yes, dog food it, but mainly to find the pain points. Lastly, it may not be as definable and quantifiable as something like correct behavior, but a user interface can still be tested. We can bring in some of our typical users, even those that don't already know our system, and have them try to accomplish basic common tasks. We can watch them, which is what's going on in this picture, and look for signs on their screens and their faces of confusion, frustration, or if we're lucky, happiness, exploration, or at least satisfaction. Afterwards, we can ask them, what did they find hard or easy, unclear or obvious? Then fix their pain points, do more of the good stuff, and lather, rinse, repeat. Next up, we have maintainability. If our software doesn't have this, then changes take longer and are more likely to introduce bugs and developer headaches. Delays could make the company miss opportunities. Bugs damage the company's reputation. Developer headaches can make key personnel quit in frustration. Any of you been there, either the one quitting or the one left behind and having to take over? No? Well, been there, okay, I have at least one person to commiserate with. Okay. We'd probably all agree that the basic idea is that maintainable software is easy to change. It's basically what I said way back in the beginning. But I'm going to add that it's easy to change with low chance of error, we don't want a dicey situation, and low fear of error, even for a novice programmer who is new to our team. Sounds pretty tough. But for better or worse, the vast majority of software engineering advice is aimed squarely at this. So as for how to achieve it, I'm just going to take two principles, fairly basic principles that go together very well, and our old standby. First up, we have good naming. You may have heard that there are only two hard things in computer science: cache invalidation, naming things, and off by one errors. Though it sounds simple, naming things is obviously hard, given the amount of software out there with really bad naming in it. I see a head nod over there. I was just going to ask if any of you have inherited code like that. I know I sure have. Even written some way back when, but that's another story. But it's very important. If we give something a vague or misleading name, then the next poor sucker to have to work on it, who may well be us, is going to have to spend a lot of their mental energy figuring out and then remembering what name in the code corresponds to what concept in the problem domain or elsewhere in the code or wherever else it has to refer to, rather than solving the problem at hand. So don't inflict that on them or us. Do the extra typing and call something, for instance, a subscription rather than a sub. That could be a substitute, a submarine, a subcutaneous hematoma. Who knows what a sub could be? The second principle you may have heard mentioned in some previous session, the single responsibility principle, or SRP. Just like a command line utility under the philosophy of Unix, each thing in our code, from the entire system down to a single variable, should be doing exactly one thing, and ideally doing it well. If it's doing multiple things, then not only is it less likely to be doing any of them well, but every use or change is going to require juggling multiple goals, which may be in conflict. So how do we tell when this is happening? One way is to go back to good names. Try to give it a good short name. Ideally one word, maybe 3, about 5 at the most. If it's hard to make it that short, or if it has to include the word and that's a dead giveaway, then it may well be violating the single responsibility principle and need to be broken up into multiple pieces. Lastly, we have our good old friend testing. Now, writing a test for whatever it is we're trying to do, like fix a bug, add a feature, or whatever, will obviously reduce the chance of any errors in that process making it into production. But also, or maybe I should say, but wait, there's more. All our previous tests from the previous bug fixes and feature additions and so forth become a regression test suite that will catch anything we break that used to work. And just knowing that that is there will let us proceed at a quick pace with a clear and focused mind, rather than creeping along slowly and carefully because we're afraid we'll accidentally break something, or, and worse yet, not find out until users start to complain. You don't want to be in that situation. And that is why I mentioned fear at all. For our final aspect, software should use resources efficiently. If we don't have this, then our programs may run slowly and make the users buy additional resources, which basically make our software more expensive, could hurt sales and so forth, or if it's an internal tool, cost our company more money, which means less for our salaries. It could clog the network. It could even crash machines by making them run out of memory or disk space. Mainly we know of different kinds of technical resources like CPU and RAM, of course, and bandwidth and disk space and disk I/O. One that's been particularly bothering me lately is screen space. Your app that should be able to run just fine at, say, 600 pixels wide should not demand to be 1500 pixels wide just because my monitor can do that. So, /rant. So how do we achieve efficiency? Just as there are lots of different kinds of resources, there are many different kinds of inefficiency. But I'm going to focus for this talk on fixing slowness. And I'm sure we've all had a program that runs slowly, and we stare at the code, spot where we think it's inefficient, spend hours, maybe days, optimizing that little piece. We run it again, and it's still slow. Anybody been there? Yeah, I've seen practically everybody. Yeah. Don't do that, measure it instead. Turns out humans aren't really very good at spotting the inefficiencies, but there are profilers and packet capture programs and on that will tell us exactly where, or at least when, we're using too much CPU or RAM or bandwidth or whatever. And in the case of things like disk space, well, you've got the data there. You can probably trace it back to where the program creates it and writes it out and so forth. Once we've found where it's slow, though, the question is, why is it slow? Certain kinds of programs tend to have certain kind of efficiency problems. For instance, a distributed system may be doing too much communication, or maybe doing it over a slow network. And that includes any web or mobile app that has to talk to a back end, and any database-driven system if the database is on another machine. Speaking of which, a database-driven system may have an inefficient query. Quick aside, how many Rails devs does it take to query a database? N+1. Ba-dum-bum. It may also be using a bad data model, like missing some indexes that would make it tolerably fast to read. It's missing them, so it's now slow. Or it may have too many indices, meaning that it's very slow to write. What's the correct balance? Depends on your use case. Similarly, it may be using a relational data model when it's actually better suited to a key value store or a document store, or of course vice versa. But in the general case, the problem is usually a bad algorithm. Maybe we're using something with a polynomial or exponential runtime when thinking about the problem from a slightly different angle, or even just settling for an approximation that might be good enough, would let us use an algorithm with linear runtime, or a root or logarithmic runtime, or maybe even constant time. Perhaps we're using a bad data structure that's forcing us into a bad algorithm, or vice versa. The upshot is that we should be familiar with the common basic assortment of algorithms and data structures, and how to analyze and compare their demands on our assorted resources, and combine them into larger structures such as design patterns and other things that may be even provided by our compilers or frameworks or operating systems. That way we can use solutions that have stood the test of time and might even be available in implementations that have already been tested and maybe even optimized. Anyway, once it's fast enough, we can slap a performance test around it. You know, I had to mention testing eventually. That will prevent us from having a performance regression. Also, there are times when we want to use more of one resource to allow us to use less of another. Some of the canonical examples of this are caching the results of an expensive computation, or something we would have otherwise had to fetch from disk, or worse yet, from another system. But sometimes we should use both more memory and more CPU to spare some other resources, mainly non-technical resources, such as elapsed time and user patience and brain power. These are some of the drivers behind things like multitasking techniques, such as concurrency and parallelism. These let us make use of technical resources that might otherwise be sitting idle, and that idleness can be considered a form of inefficiency. For instance, suppose we have a web application that generates a report. The user can sit there and read it online, or they can download it as a PDF. But the PDF takes a few minutes to generate. Don't make the users sit and wait through that, draining the non-technical resource of their patience. We can put the PDF requests in a queue and have them generated in the background, or even overnight if it's low enough priority. If our system has any sort of messaging to it, we can send them a link to their PDFs when they're ready, or better yet, if we have their email addresses, we can just send them the PDF, delete our copy, and save our disk space. And that was the last aspect, so now I'll answer the first most frequently asked question, and that is, okay, these tips are great, but how do we actually use ACRUMEN itself? That is to say, the list. Mainly, we can keep it in mind as sort of a mental checklist when writing software or evaluating someone else's. We can ask, is it correct? Is it robust? And so forth. Often, though, it won't be really a binary yes-no question, but still we can ask, for instance, how good is it on a scale of 1 to 10? or in the form of a simple triage of good, bad, or medium? Or is it good enough for our needs? And if the answer is ever that it's not good enough, then we can ask, what can be done to make it so? In the more immediate term, we can ensure that our current projects are likely to meet these criteria. In the longer term, we can ensure that our processes support these criteria. For instance, we've seen that stakeholder feedback and tests help with a lot of the aspects. So we can ensure that our current stakeholders have given us thorough feedback and verified that we're doing the right thing and that we have good test coverage, and that our processes incorporate getting user feedback, writing tests, and possibly even an evaluation against the ACRUMEN criteria. In conclusion, if our software is appropriate, correct, robust, usable, maintainable, and efficient, then nobody should have any cause to be sour about the fruits of our labor. However, one last little word of warning. Next month, I'll be leading a discussion titled Defining Aspects of Software Quality at the Software in Practice Conference at the British Computing Society. We'll be using ACRUMEN as a starting point, but we may well wind up with something different, which means keep an eye on this page up there, which, if ACRUMEN changes or is replaced, I will have that redirect to something else, or at least tell you about it. Now it's your turn. If you have any questions, I'll take them now. If you have any feedback, actually we have a good amount of time, so I'll open it up for comments and feedback as well. So if you think of something later, there's my contact information up there. And a shout out to TopTal, whose speakers network helped me prepare and practice this presentation. And please use my referral link there. That's the important bit at the end, if you want to hire them or join them. So, any questions?
Yeah, I have like two.
Okay.
Yeah, one is like, where did this origin? Because it seems like it has come up with, like, the acronym came after all this, like, okay, these are the defining characteristics of how software should be built. So I'm more interested, because I've never, before today, and not heard this acronym.
Okay,
And
well,
secondly,
to answer your first question first, it came out of right here.
Oh, so you are
Yeah.
the creator.
Yes, a
Good.
few years back, I was looking for a decent definition. Like I said, didn't find anything, and decided I might as well make my own to at least explain what I meant by it when I said, hey, I write high quality software. Yeah, what does that mean? So I decided to start with the general approach of a list of aspects. I looked at what I had said previously to refer to how I, or at least what I try to make my software like, and came up with eventually the terms correct, robust, maintainable, and efficient. Did a little more research, trying to figure out, okay, what did I leave out? Maybe my software isn't quite what everybody would consider high quality. What would be, a good overarching set of definitions? And that's when I added in the bit about appropriate and usable. Most of my software is back end, so the usability is not quite as important. But if one sort of stretches the definition beyond a user sitting there and looking at it to things like, okay, the front-end developer using the API I supply and so forth. Okay, yeah, it still needs to be usable. So I then put it out for some comments on Twitter and Facebook and whatnot, and wound up doing some wordsmithing and coming up with the term ACRUMEN. Or at least ACRUMEN, and then I looked for words that contain that, and ACRUMEN was just about the only thing. If you leave off the N, actually, I could have just called it ACRUMEN, but that's a fairly common username on a lot of systems. Like people with the last name Krum, first name like Alex or Abby or whatever. Okay, second question.
So now third question. So the second question is like how old or like how many years has this been in the industry, or is it like recent?
Oh, this is quite recent. I don't remember when I first started trying to formulate this, but I would guess somewhere about 3 years ago.
That's great.
And
So one of the slides had this. You mentioned about performance testing, and you had this rocket ship or a NASA.
Yes.
I did not follow that. Like what were they testing there? Before this, yeah. Before
There
the
we go.
multi-rail, yeah.
There. Oh, come on.
And I like the puns. By
There
the
we
way.
go.
I really like the timing and the pun, and that was like really awesome.
Yeah, that's a rocket engine being subjected to its performance test.
Oh, for the I guess re-entry. Oh, I see. Okay.
I think this was something that predid. Well, it's NASA, so it's not.
It's not
like
a capsule,
SpaceX.
it's part of the engine.
It's engine.
Yeah, it's
Yeah.
the engine, it's not
Okay.
a capsule, it's part of the engine
Got it.
that goes at the bottom of a rocket.
Yeah, I mean this here is just the nozzle.
Alright. So yeah.
So you can get a bit of a sense of scale here if we assume that this railing, well, if we assume that this is a railing that might be about yay high, as is typical on the go walk around something.
Thank you.
Okay. Any more questions? We have about 20 minutes almost. Or would you all rather just get out early?
One thing I just wanted to make a comment when you were describing them, I just kind of put together different things that I'd done in my career, and think about how these things kind of relate to what I've been doing as a programmer.
Good. That's one of the things I'm actually trying to spark in people's minds. Like, oh, I didn't realize that was so important. Oh, I totally nailed that one. Yeah, whatever. And maybe, well, especially, oh, that's an idea. I can do that next time and do better on this aspect.
Yeah, I find it very useful. For example, if I want to start a new project or something, it's a good checklist of what things we need to do to deliver some good product or something. So keep in mind, just check what we are doing correctly or what we are missing in our process.
Yes, in fact, I'm trying to work up a set of consulting services, including basically a process checkup to make sure your processes support these criteria. See what you're doing along those lines and see what I can suggest. Didn't mean to turn it into even close to a sales pitch. That seemed relevant. Any other questions, comments, concerns, character assassination?
Actually, it's pretty good.
Thank you.
You are prepared. Awesome.
Thank you. This is not the first time I've given this talk. Actually, it's the first time I've done it at a conference in the US, but I just did it at a conference in Moldova last Saturday, and in Poland last year, and in the DC area, several little meetups that were basically practice runs for Poland.
Thank you.
So, if there are no more questions or comments, then I guess I'll let you go get some soda or whatever, and it's been almost exactly an hour. So that helps me know the time. And the contact information, just in case anybody needs that.